Okay, so let's look at the other type of line integral that we mentioned last time, and this is line integral of a vector field. Well, what does it mean? So really, the thing is what do we want to do? What's the application? So the application is bigger, well, or maybe one of the applications, one of the motivating applications, is to figure out work done on a particle moving along a certain path by a force which is given by the vector field. So you have a vector field. So at each point you have a certain force, right? And then you have a path which is maybe let's just call it C, but we'll have a parameterization by C of t, right? So there's a particle, right, that's moving along this path, and this force is acting on it, right? And we want to figure out how much work has this force done on the particle. And what's work? Work is force times distance, right? So what we want to do is basically see what that is at each little point, and each little piece of this this path, and then sum it all together. So that will give us an integral. So if we're over here and the force field F is this vector field, so it's at this point it's this vector. What we want to do is, well, we want to figure out what's the component of that force F along the tangent to the path, right? Now, tangent to the path, there's some, maybe let me draw this large. Maybe this is length 1, right? This vector over here, right? So let's call it t, right? It's going to be a unit tangent vector, right? So t is going to be of size 1, and it's pointing in the direction in which we're traveling. And then we want to project our force onto this direction that's tangent, right? And so we want to figure out what is this. Well, this length, the component of the force acting along t, because t is of 1. If you remember from early on in the semester, this means it's this length is f dot t, right? So what we want to the integral that we want to compute is going to be the integral around C. It's going to be an integral of a, we're going to write it as an integral of a function we read like this, where this is the little s from, if you remember from last time. This is what's inside is a scalar valued function, right? Because f is a vector field, so that's for each point on the curve. It's a vector. T, again, for each point on the curve, it is a vector. I dot these together, I get a scalar, right? So I'll get, for each point on the curve, I get a scalar, and I integrate that over the curve, right? Now, one way we write this is, sort of a shorthand that you'll see is so that the t is not there in this notation, but that's just what it means, right? This thing that's just a shorthand for this, right? Now this, if you look up online or in books, this might not be, and actually in our book it isn't. It doesn't have the arrow. If you remember, we're drawing arrows, but in the book it's bold letters, right? So it's a bold little s over here, right? And this is a dot product, right? So d bold little s is really, really we're thinking of it as the tangent vector times ds, right? All right. Well, we write down, if we have this c of t. Let's suppose it's in two variables. Just for simplicity, now we'll write what it is in three variables as well, right? Then we have this, and we have I'm going to write over there, but t is between a and b, right? T equals a, we're right here at the start, and t equals b, we're right at the end of our path, right? So now over here, the way, well, we just write down, this is from last time, the definition of what this means, right? This is the integral from a to b of f dot t, and now we have what's this speed, right, times dt, right? All right. Well, what is this t, right? Well, this t, it's also really a function of a point on the curve. So it's really a function of t. Okay, there he goes. Allergies are terrible this time of year. So if we have if we have this t, we can think of it as a function of t, right? And well, we know that velocity points along the that points in the direction of travel, right? So that's tangent. But now we want the unit tangent, right? We want the magnitude to be 1. So we want to divide by the magnitude, right? The speed, right? And so this vector, right, is going to be the tangent, the unit tangent vector, right? So, well, let's write that in a b f dot, and now let me put the c t prime t then c prime speed again, and dt, and hey, this cancels, right? So this is actually equal to, and this is the thing that we would actually compute. The way you compute it is u dot f is the velocity, right? So that's really the thing that we compute, and you can see that this integral is a lot easier, or you're going to see that it's a lot easier to compute than a general line integral of a function where where this speed did not cancel out, and we had this square root. Even for fairly simple examples, it seemed a little nasty, right? So, okay. Now, what is this? Since I wrote this in coordinates, let me write f, and let's suppose it's just a we're just in the plane again, right? So f is well, it has two components if we're in the plane f1 and f2, and so what this thing is maybe f1. Now this is a function of x and y, right? So there's x. Well, x is a function of t. Y is a function of t, right? And then we have the first component of c prime, right? C prime is this vector that's sorry, the x prime of t, y prime of t, right? So if I'm dotting this vector with this vector, you get this dot times x prime plus f2 x of t y of t y prime t dt. Don't forget the dt, right? You may have noticed that once we're dealing with more variables, it's really important to not forget the dt. Otherwise, you don't have you don't know what you're integrating. Okay, so this is fairly easy to compute, right? You just plug into this formula. We'll do a couple of examples. Now, this is sometimes another way of writing this. So all this another notation for this is f1 dx plus f2 dy, or maybe we'd write them of x and y, right? So maybe I'll write it as f1 xy dx plus f2 xy dy, right? And this sort of tells you, how to, this notation. One of the nice things about it is that it tells you exactly how to integrate, right? Because it tells you what dx is. Dx is well, what it was? It was x prime dt, right? Or maybe another way of writing it is it was dx dt dt, right? Hey, that looks basically just like a regular sort of change of variables, right? I mean, if I go over here and I think of a change of variables from x and y to t, well, I would this would be how the dt dx changed into the dt, and of course the dy would change in the same way. It was the dy dt dt, right? And that comes into here, and that's precisely this formula, right? So all right. So let's let's compute a couple of examples just in the plane. So maybe we have let's suppose that my f is going to be let's say xy, right? This is this vector field, radial vector field, which just points outwards, and it just points out further and further. The further and further I am from the origin, right, the longer it is, right? The larger magnitude it has. All right. So now let's say we integrate this. Let's say C is the unit circle. Traveled counterclockwise. Maybe something that I didn't quite mention, but over here, this does depend on on which direction we're traveling, right? It doesn't really depend on the speed. It's because it's really the force, distance, right? So it doesn't really matter the speed along which we're traveling doesn't come into this formula, but the direction does, right? T points in the direction of travel, right? So it either points this way or it points this way. There's basically two orientations that we can take. So we always have to say exactly which direction we're traveling along. So, all right. So we have our C is this circle, and we're going counterclockwise. So how can we parameterize the unit circle? This standard parameterization, cosine, sine, right? T is between 0 and 2 pi, right? So let's integrate. So f dot ds, right? Let's do this thing. Well, it's really going to be the integral from a to b of so this is my x, right? This is my y, right? So f is cosine t sine t dot, and now I need to do the c prime, right? And c prime as well, I have cosine, the derivative of cosine is minus sine, and the derivative of sine is cosine, right? And so I put that here, right? So minus sine t cosine t dt, right? That's the f, right? Dot c prime dt. Okay, so now if we do this, right, we have cosine t times minus sine t plus sine t cosine t dt, and that's just sorry, not ab, it should be 0 to 2 pi. Sorry about that. But it doesn't really matter. The whole point is what's inside is 0. So this is 0. And that makes sense. If I look at this picture, I'm traveling like this, right? And so the tangent vector, right? This is my t. I guess it's not easy to see anymore. This is the t, right? It's this vector, right? It's precisely orthogonal to f, right? So if this is f, right? That means that if I project f onto t, I get 0, right? Another way of seeing this is that if the force is acting outwards from the origin, and I'm going in a circle around the origin, then this force is not doing any work on this particle, right? It's not, it's trying to push it outwards, but it's, the particle is just moving along this circle, and so it's sort of like inverse gravity, right? I mean, if this was, you would get the same thing as if you had something pointed towards the origin, right? It would again be orthogonal, and that it's sort of when you're running around on the surface of the Earth, the gravity is not really doing any work on you, right? I mean, it's it's not moving you from a point to point unless you're going downhill. But if you're on a flat piece of the earth, it's not it's not helping you move anywhere, right? So that's why we're getting 0, right? Well, let's maybe change the f. Do another example. Let's maybe do f is let's do minus yx, right? And so this is that vector field that was rotating around, right? That where you were getting if I'm somewhere over here, let's say at 1, 0, right? I get 0, 1, right? And at let's say at 0, 1, I get what I get at 0, 1. I get minus 1, 0, right? So I get this, and over here I get this, and I'm getting something that rotates, and it actually rotates along the direction in which c is traveling. Let's look at the same c, right? And let's integrate f.ds. Okay, 0 to 2 pi, right? And now we have to put in this f, parameterize same c, right? C, we're doing the same, right? So cosine t, sine t. So we have minus y, right? So minus sine t, x cosine t. All right, and now dot c prime. So that's the same thing as over here. And well, it's actually it happens to be the same as this by chance, right? So if we do this, dot product, we'll get minus sine t times sine t. Well, sorry, minus sine t, right? Plus cosine t times cosine t dt. So it's sine squared plus cosine squared, that's 1. 2 pi. And 1 dt is 2 pi. Right? Now, it makes sense that this is some positive number. Right? The work done on our particle has to be positive. Right? I mean, the force is trying to move us exactly in the direction of travel along this circle. So we should get a positive number. Now, if we took if it was if f was pointing in the opposite direction, or maybe if we change the orientation of the circle, if we traveled counterclockwise rather than clockwise, if we did one of those two, if they were working against each other, then we would get minus, right? Minus 2 pi. But in any case, we're basically getting that that the force, this force actually did some work on us. I mean, this is a force that's going. If you're running around the surface of the Earth, this would be a force that goes not down towards or away from the center of the Earth. It goes across. It's wind, right? And so if you're in Oklahoma, if it's windy, as it is quite often, then the wind is doing work on you, right? I mean, if you run along with the wind, the wind is helping you. If you run against the wind, you have to work against the wind. I mean, the wind is doing work on you, right? It's making you work harder, right? I mean, sometimes I get this, both ways biking to the office. I bike, against the wind in the morning. If it's blowing, south, and then if it's blowing north, and then in the afternoon, then I'm going against the wind as well. Sometimes it happens that it helps me both directions, right? So that's the idea, right? Now, this thing works in 3 dimensions just as well. We have in 3 dimensions, of course, the path is 3-dimensional. There's an x, there's a y, and there's a z, right? And we have our vector field also has 3 components. It has f1, f2, and f3, right? And so we can, if we write this as t is again going from a to b. So if we write c, the integral along c, f dot ds, it's going to be again f dot c prime t dt. It's the same computation, except now when I write this out, and let me write that out, I'm gonna have f1 x of t, y of t, z of t, and now it's gonna be x prime of t plus f2 x of t, y of t, z of t, y prime of t, plus, wouldn't fit that over there, f3, x of t, y of t, z of t, z prime of t, right, that's this parentheses over here, dt. Alright? So, it's the same thing. It's exactly the same thing. And again, we have that, we can write this as f1, we don't write of the x, y, and z, f2 dy plus f3 dz. And again, this notation tells us how to actually integrate it, because again, dx is dx dt, dt, dy is dy dt, dt, and dz is dz dt, dt, right? Precisely, the same as before, except now there's a z component, right? So you do a simple example. We let's let c t, let it be t squared t cubed, right? Where t is between 0 and 1, and so that's my curve c, and let's f f of x, y, z be let it be x, y, z squared, x, z, I don't know, something. I'm just making things up. Suppose that just happens to be the vector field, right? And so now if I do s, and let me write it in this notation as well. You might see the same equation without, we could actually replace this f1, f2, and f3 with these guys. So it's the integral over c of x, y, dx plus z squared dy plus xz dz, right? So you might see it as using this formula, or you might see it as this formula. They're the same thing, just different notation for writing down exactly the same thing. So what is this? Well, this is the integral from 0 to 1 xy, so x times y, so t times t squared, right? So the times, not a dot product, just the times. Or maybe let me write it with parentheses, maybe it's easier. Times dx, right? So dx is so c prime. Let me just write the derivative over here. This is x prime, right? So that's 1. Y prime is 2t, and z prime is 3t squared, right? So over here I'm gonna get times 1, right, plus z squared, that's t cubed squared, dy is 2t, and now we have xz, so that's t, z is t cubed, and dz, so z prime, right, z prime, is 3t squared, right? And this whole thing is back to dt. So we can simplify this a little bit. I have t cubed over here. Then over here I have 7. This is degree 7. Yeah. So I'm gonna have plus 2t to the 7, and then I'm gonna have 3 t to the 6, right? And so this is gonna be 1/4 plus 2/8 plus 3/7. Right? I think I'm doing that correctly in my head. Right? That's just a calculus 1 integral now, right? Okay. So it's all rather easy to compute. Right? Much easier than the regular line integral of a function, right? Now, of course, yeah, you can't in the real world, right? If you're trying to solve a certain problem, you don't pick the problem to be easy to solve. You solve the problem that you have to solve, right? If you have to build the bridge, you have to build the bridge. You can't say, well, I'm gonna build something else because that's easier, right? All right. But fortunately, this kind of integral actually does maybe come up actually even more often than the integral of a function, strangely. So another notation, just so that sort of more of the complete notation, is sometimes if I have a c for a curve, minus c is the curve in reverse. So maybe if a curve c is I'm traveling this direction, the same curve but traveling the opposite direction is minus c, right? So for this, it's basically that's going to flip the t, right? So if I want to integrate along the opposite direction, it's just going to flip my sign. And that's basically the same thing as integrating from a to b or from b to a, right? That's basically the same idea, right? So just a notation for this. It doesn't mean I'm actually taking minus of some number. It's just a notation that says I'm gonna go in the opposite direction, and the reason for using the minus sign is because the minus sign is here, right? I mean, we could use some other notation for this, and some people do, but minus sign seems reasonable. So that's one thing. Another thing that about this integral, it is linear. So if I have two vector fields and I do a linear combination, a times f plus b times g, right? And I integrate this thing along some c, then this is the same thing as taking a times the integral of f plus b times the integral of g. Right, so that's exactly the way that we've had this before. Another thing that's useful in computations is that if I have a path, let's say C1 that goes from here to here, and then maybe C2 that goes from here to here. People sometimes write this path, that putting this together as C1 plus C2, right? Means we traverse C1 first, and then we traverse C2, right? So the little particle is traveling first along here, and then it's traveling along here, right? Then what people write is that if I traverse, if I do this path, and again, if you think about the definition, it didn't really matter exactly how we parametrized the curve, right? Where t started, where t ended, as long as we went in the correct direction, right? So you can parameterize this thing however you want. Maybe you can parameterize it in the same way as C1, and then then start over here and go with C2. You can use both of those parameterizations. Maybe you have to sort of shift the time for one of them. It doesn't really matter how you parameterize, but somehow this is the total path. So then this integral, well, is just going to be, no matter how I parameterize, as long as it was this path, this guy parameterized the total path, I could have just integrated the pieces, right, and added up. And that's really the same thing as in one variable. Integrating, let's say from 0 to 1 and from 1 to 2 is the same thing as integrating, if we add up those integrals as integrating from 0 to 2, right? That's basically the same idea over here. Okay. Now, the final thing that talk about is maybe slightly different way of, maybe let's do a new page, because it's kind of a different thing. Is talking about flux, and so this, as a line integral, this only makes sense in the plane, so in 2 dimensions. So if we have some curve C, we could look at, instead of the tangent vector, we could look at a normal vector, right? And we could make this the unit normal vector. Now, there's of course two ways of doing this. So this is one way. I could also look at the other direction. That would also be a normal, but somehow we're thinking of one orientation of this, right? And so what's flux? Flux is basically, we look at the vector field and think of it maybe as a flow field. So maybe think of it as a flow of ocean water or something like that. and we want to see how much water goes across this line, right? If the water is flowing along the line, no water is going across the line. If the water is going directly across, then there's a lot of water, right? If the water is going the other direction across, then we should get a negative quantity. So this is the so-called flux integral. And there's a similar one in 3 variables, except you have to do a surface integral instead of a line integral. So as a line integral, it only makes sense in 2 variables, right? Because a line, I can't really think of in 3 dimensions, what does it mean to flow across a line? It makes sense to flow across a surface, right? Across some membrane. But on the plane, a line definitely separates the plane into 2 regions, one side and the other side. Right, so I can say how much stuff goes from here to here, right? And so, so for this, what you need to know, oh, actually, I'm now looking. I've probably used different notation than in the book, and the notation is not completely standard. So I guess in the book we're using EN, if I'm copying from the book correctly, right? It's the normal component of the well, the E meaning for the unit, right? Why is E unit? That's from German, eigen, right? So, all right. So if we have the normal vector, however we write it, right? The flux integral is f dot en, right? dt, right? Now, so ds. We haven't yet parameterize it, right? So now the thing is we need to figure out what is e to the e sub n is, right? So there's 2 choices. One way, and I guess that's the way I've written the notes. I assume that's the direction that the well, that's one way of writing it. This is just the norm of this vector. That is a normal vector, right? One of the 2 normal vectors, right? The other one is just negative with this. So this is maybe let's look at so the tangent vector is x prime y prime, right? So if we're going along, let's see which one we're getting. If we're going along this direction, and this is t, right? Then if this is t, so for example, if maybe I should draw. Sorry, I draw. This is t, but let me draw this. It will be easier to figure it out over here. It's basically the vector would be 1, 0 over here, right? So if it would be 1, 0, then this would be 1, 0, right? So that means that this is 1, this is 0. So I have 0 minus 1. So this is the E, right? You always have to figure this out so that you know which direction what sort of flux you're computing. So for example, over here, we really, it would be as if we're if we'd have this tangent, then it would be the tangent would be pointing out this direction. But we're not integrating along the tangent, so for the flux, it doesn't really matter, right? But if I do, if I want to use this guy instead of the minus, then I have to parameterize this direction. Otherwise, I would have to put a minus sign over here, right? So once I know which direction the normal is going, and I mean, if you get it wrong, you just get it off by a minus sign, right? So it's not a big deal, of course, though. You know, if you're trying to figure out how much water flows into a certain bay, right, and you're getting minus, well, then it just means it's flowing maybe out, and you're thinking it's flowing in. So maybe that's quite a bad of an error. So you have to, yeah, I guess you have to be careful about which one you're getting. And you really have to, you know, the best thing is to draw a picture. You know, actually try to figure out, you know, from the formula, where does it point? So for example, we could look at, you know, if the flow fields, if f was, you know, x y, and we want flux across. That's terrible. Do you put two C's in across? Maybe. I don't know. Across. Yeah. Two S's, definitely, right? Across the unit circle. You know, maybe outwards. You know, it's just you know, we want to figure out the flux as we're going from inside out. And actually, this is a fairly normal, you know, fairly normal way to do this. If I have you know, a closed loop, some sort of, maybe a circle, maybe some more complicated thing. It's we're usually thinking of you know, the it's sort of semi-standard that people think, well, then the normal should be pointing out, right? That's just you know, a good you know, just a way to sort of, you know, people agree with each other, right, on this. So anyway, so let's think of, you know, we have this unit circle. We have we can parameterize counterclockwise, because as we saw over here, it's this formula will move 90 degrees to the left, right? So if I move 90 degrees to the left, I'm pointing outside, right? So if this is my e to the e sub n, right? So C is cosine t sine t, right? Going counterclockwise, right? So the this integral is well, we're gonna integrate from. By the way, I should write it down. I wanted to write it down over here, and then I, you know, forgot. You know, how does what is this ds, right? This ds is right. This is this y prime minus x prime divided by, well, you know, this is the you know, if C parameterizes the path, then this is divided by the speed, right? Just like before. Right. and then the ds is the speed, right? So these things cancel, and so the general formula is just y prime minus x prime dt, right? These are functions of t, right? So over here, t is, if we're going once around the circle, 0 to 2 pi, so 0 to 2 pi f. What is f? F is xy, right? So cosine t, sine t. What is c prime? So x prime is minus sine t, y prime is cosine t, right? So now I have y prime, so cosine t, minus x prime sine t, right? So this is this guy, that's this guy, this is this, right? And so what is this? Well, this is, again, we're gonna get cosine t squared plus sine t squared dt, and that's 0 to 2 pi 1 dt, so 2 pi. And, well, it's, it makes sense. This is the flow field that's going, outward. So stuff is flowing out, right? And it's flowing out at this rate, right? So, all right. Now, this is used in other applications. This sort of integral. It's a way of if you figure out for an electric field, right? You can using this flux, you can figure out how much what's the charge inside this inside this circle, let's say, or inside some closed loop, right? So this is one way to figure out how much charge is in a certain region. It's it's gonna be basically how much flux is going across the this boundary, right? This circle. Okay, so that's good enough for today.